I think if it doesn't show, as Orlando alluded to, this is just such a fun part of being on the MRS officers and just helping celebrate all of this hard work. So we really enjoy it. Before I introduce the next award, the Von Hippel Award, I do want to remind everybody this evening that we are capturing the talk, and all of this week's awards talks have been captured by MRS on demand. So if you missed any of these wonderful speeches, you do have the opportunity to go back at our website and review them and share them with colleagues and loved ones. So at this point in the program, it's my true privilege to introduce the Von Hippel Award. The Von Hippel Award, as you know, is MRS's highest honor. It's conferred annually to an individual in recognition of the recipient's outstanding contribution to interdisciplinary research and materials. Marvin L. Cohen from University of California, Berkeley is our awardee this year, and I'd like to share a little bit about him. He's a professor of physics at Berkeley and senior faculty scientist at the Lawrence Berkeley National Lab. His current and past research covers a broad spectrum of subjects in theoretical condensed matter physics. He's a recipient of the National Medal of Science, the APS Oliver E. Buckley Prize for Solid State Physics, the APS Julia Edgar Prize, the Foresight Institute Richmond Feynman Prize in Nanotechnology, the Technology Pioneer Award from the World Economic Forum, the Berkeley Citation. If you can't imagine, there are several more sentences of very great honors here, as well as doctor honors degrees from the University of Montreal, the Hong Kong University of Science and Technology, and the Weizmann Institute of Science. He's contributed more than 800 technical papers, publications, and is one of the world's most cited physicists. He's a fellow of the American Physical Society, a member of the National Academy of Sciences, the American Academy of Arts and Science, the American Philosophical Society, and a fellow of the American Association for the Advancement of Science. In 2005, he was president of the American Physical Society, an organization representing more than 47,000 physicists in universities, industry, and national labs. It is our great honor to induct him as this year's Von Hippel awardee. Please help me welcome him to the stage for this evening's lecture.
Thank you. Thank you. Is this on? Can you hear me? Okay, good. Thank you for that kind introduction. It's a pleasure to be here, and it's a great honor to be the 2014 recipient of the Von Hippel Award. And next year I'll be 80, and my best work is ahead of me. And I have an inspiration from Von Hippel, who lived to 105. So I have 25 years of work ahead of me if I can figure out the secret of Von Hippel. Well, tonight I'm going to talk about explaining and predicting properties of materials. I'll try to give you some idea of what we do. And since you see quantum theory up there, it must be clear to you that I'm a theorist. Now, to give you some idea of what we do, experimentalists discover the secrets of nature. They measure the properties and report them. And theorists, our domain is trying to explain those properties and to predict new properties. So it's a little like this cartoon where the experimentalist is in the middle and he says, to be honest, I never would have invented the wheel if it were not for Erg's groundbreaking theoretical work with the circle. So Erg is on the side, and I identify with Erg. And if you look on the ground, there's a lot of circles, so Erg had a lot of theories that didn't work before he finally got to the right theory for the wheel. Now, the most important concept in all of science is that macroscopic matter is made of atoms. And this was not believed by all scientists, even back at the beginning of the 1900s, even though the concept went back to the ancient Greeks. And in fact, Einstein's PhD thesis on measuring the size of sugar molecules was quite important, and this work helped to verify the fact that molecules and atoms existed. And later, when people began trying to explain the properties of atoms and realized that they needed the quantum theory, they relied a lot on the example of Einstein's explanation of the photoelectric effect. And that was his Nobel Prize-winning work. And that helped establish quantum theory. So the most important concept is that matter is made of atoms, and that atoms have to be explained using quantum theory. So our current picture of an atom is roughly this. There's a positive nucleus surrounded by electrons that are held close to the atom. These are the core electrons. And then these fuzzy things on the outside are the valence electrons. So if this were silicon, the nucleus would be a plus 14. The core electrons are, there's 10 of them, so they're negative 10. So this core is basically plus 4. And it doesn't change much when you build a solid. So when you go from atoms to solid, the core remains sort of intact. So the objective of a theorist working in condensed matter physics is to explain the properties of the valence electrons and how the valence electrons move around and form the solid and give the solid its electrical properties. The thing is that if you're dealing with quantum mechanics, you can only predict things in terms of probabilities. And so we can predict the probability of finding an electron in a specific place very precisely. Now, in 1929, Dirac, who contributed greatly to the development of quantum theory, posed what we call the Dirac's challenge. He said that the underlying physical laws necessary for a large part of physics and all of chemistry are completely known. And the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. Well, my job is to tell you what we've done to answer Dirac's challenge. Now, at the beginning, people worked very diligently on the optical properties of gases because then they could deal with individual atoms. And this was critical for establishing the quantum theory, and it also explained the properties of atoms. But the solid-state spectra, I'll show you in a moment, are broad. And so these spectra were very difficult to interpret. For example, if you looked at absorption spectra for atoms and gases, you see very narrow lines, and you could explain these in terms of transitions of electrons between different atomic levels. The separation of these two lines is about 20 millivolts. In contrast, if you look at the reflectivity of a solid, and here are 3 different semiconductors, as a function of energy, the scale here is electron volts, and the resolution that you saw in the last slide is less than the width of this line. So these broad features are not so easy to interpret. Now, when people started to classify solids, at the beginning they looked at their mechanical behavior. After all, a solid is solid. And in fact, to determine what solid was the hardest, they took a solid and scratched it on another solid. And the ones that ended up unscratched were the hardest ones. And this was in the 1800s, and there's a scale by Mohs, and diamond is a perfect 10. And that's the hardest material we know. although there's no ratio of physical constants that gives you 10, but that's the scale. And then things became more sophisticated. People began to look at the chemical composition of solids and classified solids that way. Then X-rays came along, and you could experimentally measure the structure, the periodic structure of a solid. However, two solids can have similar periodic structures, but have very different properties. So, the experiment that really classified different solids and gave us great insight into the properties of solids was the resistivity. Just measure the resistance of everything in the world, and you'll find out that not only is it a wide range of values, in fact, over 30 orders of magnitude, but you'll see in a moment that they group. So in everyday life, we see copper, which is a good conductor, so therefore it has a very low resistance, and quartz, which has a very high resistance. And if you measured all the materials, you'd find that we have metals. Copper is a good example, and this is roughly the value of the resistivity. Then there are a few materials like bismuth, which are semi-metals, semiconductors, which have a wide range of resistivities depending on what impurities you put in, doping, and insulators. And these have they're very reluctant to conduct electricity, and so they have a very high resistivity. Diamond's a good example. So this grouping and the fact that materials can be so different, the explanation of this was a triumph of electronic structure theory. And it's explained in the following way. If you take a box and fill it with electrons and ask what happens to the electronic structure, you find that because of the quantum nature, these electrons are in various levels. And you can look at these levels, and they'll be separated because of the quantum theory. And if you put two electrons in each energy level, because the Pauli principle says you can put a spin up and a spin down electron in each level, then if you have an even number of electrons per atom or per cell, then you fill everything up. And then if there's a gap, if you try to put an electric current on or you shine light on, the electrons have to jump the gap in order to conduct. If there's no gap, then there's no gap between the occupied and the empty state, you can easily get an electron to conduct. And that's a metal or a semi-metal. And that energy place with the separation of energy between the occupied and the empty level is called the Fermi energy. So with this picture of filled electrons and empty electrons, you can explain these properties. Small gap is a semiconductor, let's say about a volt, 1 electron volt. If it's 10 electron volts, it's an insulator. And if you take an electron from here and put it into this state, then it can conduct. And if you take it all the way out, up to high energy, it can get out of the crystal, and that's the photoelectric effect that Einstein received the Nobel Prize for. So, the resistivities can be explained in terms of states very near the fundamental gap or near the Fermi energy. But most of the properties require a knowledge of the electronic structure of a wide energy range. You have to know all of those occupied levels and the empty levels. And this is obtained by studying the optical properties, because you can look at how electrons go from occupied states into those empty states. And in the 1920s and 1930s, although there were significant advances were made in studying models of the kind I just said, a box of electrons with a smeared out positive background to represent those cores or the lattice. These models were idealized, and they didn't tell the difference between different materials very easily. And in the 1940s to 60s, people tried to do calculations on real solids, the kinds of materials that everybody's working on here at the MRS meeting. However, progress was very slow. Now, theoretical work on these models advanced at a rapid rate. In fact, in 1957, when advances like the theory of superconductivity by Bardeen, Cooper, and Schrieffer, which explain the properties of some metals at low temperature that have infinite conductivity. Electrons can go around in a circle forever, the age of the universe, as long as you keep it cold. There was still no accurate, detailed knowledge of the electronic band structure of silicon. Now, by band structure, I mean the energy is a function of momentum or wave vector. And the breakthrough came with a detailed study of the optical data. So, in the mid-60s, we were able to compute the electronic band structure of 14 semiconductors at a period where people didn't know any, just because we were able to analyze the optical properties. And in the 70s, the physics of the optical structure of semiconductors was solved, and in the 80s, people extended the methods that were used in the 60s to do so-called ab initio calculations. EPM stands for empirical pseudopotential method. It means that we take in 3 parameters from the data, optical data, and can explain the optical spectrum. Ab initio means, that we actually can start with just the knowledge of the atoms and calculate all the properties of the solid. And from the 1990s on till now, people are doing complex materials, calculations for complex materials, using these methods, and sometimes predicting the existence of materials before they're found in the laboratory. So what were the breakthroughs? Well, computers helped a lot. New physical pictures of what was really going on were very important. And better optical spectra. In fact, the big breakthrough was, instead of just measuring the reflectivity of a solid as a function of energy, one would take a derivative of that reflectivity, and that derivative would show all the detailed electronic structure. And as you see here, theory and experiment are in very good agreement. This discrepancy was explained later as due to so-called exciton effects, and out of all of this structure was explained using only 3 parameters to determine the electronic structure. So let me step back for a moment and tell you how to think about this. There are 2 popular standard models of a solid. And the one I'm talking about here is you start out with atoms and then put them together into a solid, and think of the solid as interacting atoms. So the solid is a collection of strongly interacting atoms, and the particles that you saw were those positive cores and the valence electrons, which can now move throughout the solid. And the only interactions you have to worry about for these materials is electromagnetic interactions, the Coulomb interactions. So the problem is set. However, there are 10 to the 23rd particles per cubic centimeter, and so they can give you complicated effects. So this would be a picture of an interacting atoms model. You have the nucleus with the core electrons, and we keep them the same as in the atom. And then the valence electrons can wander around. If this was a covalent semiconductor, the negative valence electrons would situate themselves between the positive cores and bond, make the covalent bond, so this would be stable. So this is the wrong structure for silicon, but it's the picture of what holds silicon together. I'll show you more accurate things for silicon in a moment. So how do we compute these things? We have to know how the electron interacts with its core. Well, I said it's electromagnetic, so if I plot the interaction, the potential of an electron coming in to a positive core, the electron's negative, it goes like 1 over the distance, the Coulomb interaction. However, when it gets near the core, remember the Pauli principle said that you can't put more than 1 electron in a state, or 2 electrons, spin up and spin down. So this electron is pushed out by the Pauli principle, a Pauli force, that keeps it out of the core, and it cancels off this attraction. And so most potentials near an atom look like this. They're attracted, and then they get weak. And if you take the Fourier transform of that simple potential and put it in a periodic lattice for systems like diamond or silicon or germanium or tin, you only need 3 parameters to give you the electronic band structure. And this is what a real electronic band structure looks like. Before, I just had flat energy levels, but now as a function of wave vector, you see that these have detailed structure. And then the optical properties comes from taking electrons from these occupied states to the empty states, and the gap is there. And this is all done with 3 parameters taken from the optical data, and explains all the properties of germanium in terms of the electronic properties and optical properties. And this was done many years ago, and it's still one of the most accurate and precise band structures available. But it has an empirical part. The other thing is we realized that not only do you have the energy levels, but you know where the electrons are now, or the probability, as I said. If you take the wave function and square it, it gives you the probability of where an electron is. So here's silicon, and there's that covalent bond that I talked about, except this is really for silicon. Here are the 2 positive cores, and you see that the covalent bond, these are constant levels of density for electrons. It makes sort of an X-shaped blob between the 2 cores. And this is the covalent bond that holds silicon together. This is the experiment, which I'm proud to say was done after the theory. And this was the first picture of a covalent bond. So the point here is that the optical properties of semiconductors originating from interband transitions were essentially explained by an international experimental theoretical collaboration in the 60s and 70s. The theoretical work was this empirical approach, and the empirical approach led to other approaches, other empirical approaches, and ab initio approaches. So, for example, by looking at the optical properties, you can actually tell something about the structural properties. Using that empirical approach, you could prove that there was an equation for the bulk modulus. The bulk modulus is 1 over the compressibility. So it can tell how compressible a solid is. So we're talking about the mechanical properties that I mentioned before. And many people here study mechanical properties. The simple formula says that if you feed in the bond length between 2 atoms in there to the 3.5 power and put in x equal 1 or x equal 2 for a 3,5 or 2,6 compounds, then you can explain or calculate the bulk modulus on a hand calculator for all the 3,5 and 2,6 semiconductors, and you could extend that formula to others. And basically, there's perfect agreement between that formula and experiment. So that's an empirical theory that came from optical properties that gives you an idea about the mechanical properties. So everything is hooked together. But a true ab initio calculation has to start with just input about the atoms. So for the ab initio approach, all you want to use is the atomic number to generate that potential, the atomic mass if you're looking at vibrations, and you test different crystal structures. And you can calculate, when you put all the atoms in their proper place, the total energy of a system. So you have the cores interacting with each other, that energy, the cores interacting with the electrons, the kinetic energy of the electrons, the Coulomb interaction of the electrons. This is electrons. The charge interaction, and then exchange and correlation, which people use the density functional theory to calculate. And if you do that, again, in this particular chart, this was the first one many years ago. Only input is the atomic number and the crystal structure. You can calculate from first principles the lattice constant to less than 1%. And usually the bulk modulus to less than 1%, but germanium is a sort of a bad actor. So with that theory, first principles theory, you only have to know about atoms, and you can tell the properties of solids. So let me come back for just 1 minute and show you the kinds of things you could explore. Here's silicon again, and this is from this ab initio calculation. There's that blob of charge that forms the covalent bond that binds two silicons together. If I go to diamond, just replace the silicon by carbon, then instead of getting a single blob, I get a double hump. I get this one and this one. And that turns out to be important. In fact, it's fundamentally associated with the concept of why you're alive. People say silicon is the basis of geology and carbon is the basis of biology, and it's because of this. In silicon, there are electrons in the core, p electrons, angular momentum 1, that push the charge into the bond. Carbon, which is in the first row of the periodic table, has no p electrons in the core, and so it doesn't push them out. So this is a double hump charge. And so carbon can form multiple bonds and make all those nice biological molecules. And all the science fiction articles of books about silicon biology are wrong. You can do this with, of course, artificial. You can make silicon devices and produce machines, but in terms of a biology, it can't do it. But here, also, you can make graphite. And as you know, graphene is a very popular material, and many papers here on graphene. And the reason is because of this nature of this bond. And I'll show you a little bit more about that later. So with this pseudopotential method, and the word plane wave is in there because these calculations start off with just a box of electrons with a constant density. You're not telling the system that it's an atom or there are any atoms there. And you just calculate the total energy. You can calculate electronic structure, the band structure, crystal structures, high pressure crystal structures, mechanical properties, vibrational properties, electrons interacting with lattices, and even superconducting properties. And I'll give you a few examples. So some quick examples. First of all, there's a lot of work being discussed here about photovoltaics. And let me just mention one area that is just starting to receive attention. What we want to do is we want to capture the energy from the sun, turn it into electricity, and solve all our energy problems. And so there's a feeling, usual approach is called band gap engineering. If you can get a semiconductor with a gap in just the proper range, then when the sun comes in, the photons will take those electrons, kick them up over the gap, and then you produce electricity. That's a theorist's hand-waving description. However, there's another approach that's probably more important, and that is called wave function engineering. In the following sense, what I'm going to show you is an attempt to use silicon as a photovoltaic. It's the most popular photovoltaic, but put it under pressure so that you get a different structure so it's more efficient. And it's not just the question of the band gap. Now, first of all, what happens to silicon under pressure? Well, there were some high pressure phases known when these kinds of calculations started. But because of the calculations and the predictions of new structures of silicon, they have grown. And we have many, many more structures. In fact, all the theoretical structures that were predicted have been found so far. I'm sure there are more that people are coming up with all the time. So, for example, if I take this material, I won't show you its structure, silicon in the Ra structure. The idea is the following. With band gap engineering, you try to tailor the band gap as a function of either alloying things together or doing various things so that the gap is in the right range. But the point is not so much that you want the gap in the right range, you want the system to absorb the sunlight in the right range. So what you want is you want to get the best absorption coefficient as a function of x. And x here is really these high pressure structures. So this is just to whet your appetite about this area. Here's the solar spectrum, function of energy. And notice the ordinary diamond-structured silicon band gap is here. And the absorption is very flat in the region where the sun peaks. Now, people who work in this field know this very well. However, if you modify the silicon, go to these other structures, the absorption goes way up. Even though the band gap hasn't changed a lot, and it can change, you get a much better absorption. So this is one of the applications I thought I'd mention. Another one would be in the nanostructure range. There's a great deal of work being discussed here about nanostructures, nanotechnology. And again, these methods work. So for example, we talked about diamond, where every carbon atom is surrounded by 4 other carbon atoms at a distance of 1.54 angstroms. But carbon, because of this peculiar bond structure, you can actually make 3-fold coordinated carbon. Every carbon atom has 3 neighbors. This is the so-called sp2 structure. So in the plane of graphite, you have these layers which are graphene, and the bonds are very short, so they're very strong. If you remember that empirical formula, it went like 1 over the 3.5 power of the bond length. So actually, if you could pull on graphene, it's stronger than diamond. However, the graphite in your pencil lead, when you run your pencil over paper, it leaves layers of graphene because the layers are separated by a wide distance, and the bonds between layers are van der Waals bonds, which are very weak, so you can pull these off. In fact, the Nobel Prize was awarded to people who were clever enough to put Scotch tape on the top of this and peel off single layers of graphene. So these systems can also be explained using these approaches. And in fact, we know that graphene layers roll up and make carbon nanotubes. And theoretically, you can calculate the properties of these. And I'll give you just one example of a carbon nanotube and one example of another nanotube. If you take a sheet of graphene, and so it looks like chicken wire with all the hexagons, and you bend it around so that you go around eight hexagons and bring it back, that material will look like this, and it's a semiconductor. So the 8 refers to the fact that I went around 8 times, but I didn't displace the system. For example, here, if I go around 7 times, but move my hexagons up 1 so they don't match, that material is a metal. And you can put the 2 of them together so that you have a defect, which instead of 2 6-fold rings, you have a 5-fold and a 7-fold. So now you have a semiconductor in contact with a metal, and it acts exactly like a piece of silicon in contact with a piece of aluminum. However, think about how small this is. And so that you can make devices on a very, very, very small scale. And this system was predicted theoretically, and fortunately, experimentally it was found. And this is another one of that kind. We were able to predict that boron nitride would form nanotubes. Now, unlike the carbon nanotubes, which sometimes are semiconductors, sometimes are metals, boron nitride nanotubes are always semiconducting, but with a wide band gap of the order of 5 volts or so. So the different boron nitride nanotubes are like the carbon nanotubes, except you have boron, nitrogen, all the way down. And they have unusual properties. For example, if I take a boron nitride nanotube, this is the band structure, and I dope it so that it's N-type, the charge goes right up the center of the tube. So it's like a pipe for electrons. And I won't go into all the details, but the point is that boron nitride nanotubes have many applications. When you make yarn out of carbon nanotubes, it's black. It's hard to dye. Boron nitride nanotubes, it's all white. It's called white graphene by some people. You can also put buckyballs, the C60 molecules, down the center of boron nitride nanotubes and do all kinds of things with them. Also, you can use boron nitride nanotubes are more bio-friendly, and they've been used for medical research. And so the big problem up to now has been that it was very hard to make these tubes, and there weren't enough around for everybody. But now there are new methods, and you can make large amounts of boron nitride nanotubes, and there's a significant research program. So that's some discussion of what you could use the interacting atoms model for. You could use it to discuss photovoltaics and also, let's say, nanotechnology. However, I want to now delve into philosophy. And most physicists, when they hear that somebody's going to talk about the philosophy of science, they leave the room. They've heard enough from these philosophers that philosophers don't even know quantum mechanics, and blah, blah, blah. But nowadays, philosophers have learned quantum mechanics, and there have been some very exciting discussions about elementary excitations emergence, and I'm going to give one example, superconductivity. So the second model of a solid is called the elementary excitation model. The first model, remember, was you put atoms together like a Tinker toy, and you build Legos and you build solids. The elementary excitation model is much simpler in some sense. You hit a solid with a probe, light, temperature, magnetic field, whatever the probe is. That excites these excitations in the solid. These are called elementary excitations. And then you measure a response. So, for example, if you're using light and you're an optical scientist, you shine light on some material and then you measure its reflectivity. If you were using heat, you'd measure the heat capacity and so forth. And you'd explain the properties of this system only in terms of the excitations that you think are being responsible for what you're seeing. So, for example, you think of a probe and response model of a solid in emergent behavior. Certain excitations emerge. And these are sort of fictitious particles, but they're not as flaky as they sound because we work on them all the time. For example, in Silicon Valley, the engineers work, some of them spend their whole career working on holes in silicon. And a hole is just the absence of one electron in, let's say, a box of 10 to the 23rd electrons per cubic centimeter. Now, it's very hard to pull an electron out and then try to explain everything in terms of what the other 10 to the 23rd minus 1 electrons are doing. But if you trace a hole, it's much easier. And that concept is real in the sense that it explains the properties of the material. Or, if you hit a solid with a hammer, you excite sound waves. These are vibrations of atoms. So you have a wave. And we know that a wave and a particle can be thought as complementary, so why not think of those waves as particles? And these are phonons. You don't get boxes of phonons and holes that you can give as holiday gifts, but they are very important fundamental concepts, and they're very useful. Now, the philosophy of some of this goes back to around the beginning of the 1900s. A very interesting person is Henri Bergson. Bergson is French, and he started out in mathematics. And he had an important thesis in mathematics, and he was doing quite well. And then he decided Einstein was wrong with relativity and argued with him. And sort of eventually gave up and went to the other side, although some of the philosophers are still talking about Bergson's concept of time compared to Einstein's. So he moved from math to physics and then to philosophy, And he said, everything we know are through images. The only reason I know you're out there is because I can see photons bouncing off you, or somebody will cough or move, and I can sense that. And so he said that this is the fundamental aspect. And so that's why people think of physical properties as emerging and these particles as emerging. It's curious that Bergson went on to win a Nobel Prize in literature. So he'd be an interesting person at a cocktail party. He's able to talk about a lot of different fields. So people talk about emergence in theoretical physics now. The cosmologists talk about the emergence of space-time. We talk about the emergence of particles. And we try to explain these systems in terms of what kinds of particles can emerge. And then there are examples of properties of materials. For example, if you take a material at a low temperature, as I mentioned, it could go superconducting. And superconductivity is considered an emergent property. Magnetism. All of a sudden, all the electrons get together and the system goes magnetic. There's the quantum Hall effects. And now a lot of work on topological insulators. I won't go into these, but I'll just give you an example for superconductivity. So here's the first picture in 1911. Kamerlingh-Onnes in Leiden and his students discovered superconductivity in mercury. They were measuring the resistance of mercury down to low temperatures, and the resistance went to zero, really zero, as close as they could measure, and they did a very good measurement. And so nowadays, we try very hard to predict the superconductors. Now, there are new classes of superconductors that are not explained by the Bardeen-Cooper-Schrieffer theory, but there are many that are. Now, how do we apply the models that I talked to you about to predict superconductors? Well, at the beginning, we used the semi-empirical models. We used the same electronic band structures that I showed you from data, but then we were able to use ab initio models to predict other materials. So there's a bunch of materials, and I thought I'd just mention what we did with silicon, and then I'll come to the end of my talk. If you put silicon under pressure, it goes into many phases. As I mentioned, some of them could be useful for photovoltaics. But an example of some high-pressure phases of silicon that are metals is that if you put silicon under pressure, you can predict that there'll be a simple hexagonal phase that's a metal and a hexagonal close-packed phase that's a metal. You can predict the existence of these materials, their stability, the lattice constants, the mechanical properties, the electronic properties, the phonon, that's the vibrational properties, how the electrons interact with the phonons, the superconducting transition temperatures and their temperature dependencies. And the only inputs are the atomic number, the atomic mass, and an estimate of the Coulomb interaction, and the candidate structures. And these materials were discovered, all the properties were correct, and they were found to be superconducting at the proper temperatures. And so in some sense, silicon, which is our prototype semiconductor, at high pressures may be the best understood superconductor. So our standard model in condensed matter theory is an interacting atoms model, which I showed you. Also elementary excitation model. Science philosophers would say that the first model is reductionism. You know what's going in there and you know the forces, that's all you need. Emergent people would say that's not all you need, because life is an emergent property. If I put all your molecules together, I don't know if you will say hello and become alive. So we take both approaches. And so nowadays, theorists can explain and predict ground state and excited state properties of many condensed matter systems, but all decisions in physics are made by experiment. We don't make the decisions. So the experimentalists still make the decisions on what's right, and they also have made all the major new discoveries up to now, and we hope we can do better in the future. Now, somebody said, are you going to say something about the future? Well, if I can learn von Hippel's secret, maybe I can work on these problems that are being discussed here. And the question of fundamental and applied condensed matter physics, what kinds of problems should we work on? Well, there are all these problems that I've heard about at this conference. Energy production, storage, transmission, make sure that the energy is clean, better materials for all kinds of applications, high temperature superconductors. We're still trying to get room temperature superconductors with trains going along at the speed of airplanes. We want to interface with biology. It's an open area, and we saw that some of the awards are going in this particular area. Information technology, quantum computing, correlated systems we want to understand better, and we want to predict new states of matter. So these are just some, but I have to warn you that Yogi Berra said predicting is difficult, especially about the future. Now, I said applied and basic. So one question that comes up often is a student will ask, should I do basic or applied science? And the answer is one should give the same answer as one gives to the following question. Is light a particle or a wave? And the answer is yes. I also want to warn you, this is the disclaimer at the end of the talk, that when I talked about theory, Einstein warned that the most valuable tool of the theoretical physicist is his wastebasket. And you saw even Erg made some false starts. Well, I want to express my gratitude to my collaborators. Over the past 50 years, I had the joy of working with outstanding students, postdoctoral researchers, and visitors from around the world. Some of them are here tonight from Japan, from Canada, from Spain, other parts of Asia and Europe. And so it's a wonderful thing to be able to work with people on things that you believe in. And finally, I want to thank the MRS for awarding me the 2014 Arthur von Hippel Award. This is a great honor, which I will greatly treasure. Thank you very much.